In 1-6, we're going to build upon the ideas you were learning in 1-5. Recall, you were looking for places where lines or parabolas, if you will, were either crossing and meeting each other when it was an equal sign, and you wanted that x value where they were meeting, or you were looking for where, say, one graph was bigger or smaller than another graph. Oftentimes, that was a span of x values where this was happening. We're going to continue talking about linear equations, and note this word here in our essential question. Equations is always going to have an equal sign, and inequalities, well, that's the alligators we're talking about, so any of those combinations of symbols. We're going to be looking at the same ideas, but this time in 1-6, we're looking at a system of them, and system, this can mean like many equations or inequalities at one time. So we're kind of stepping up our game. Let's look, for example, here at example 1. They say, what is the solution of the system of linear equations? Now, you can graph these, and one way I like to encourage my students is you can think about if you make x be 0, for example. If x was 0 in this equation, you would just have 2y equals 3. We could solve for that, and we would say 2y equals 3. Well, that means y, if I divide by 2, y is 1.5. That gives me my y-intercept. Now in this equation, so this was all the top one. In this bottom one, if my x was 0, I'd have negative 2y equals 4. If I divide by negative 2, I would get y equals negative 2. That would be my y-intercept. Now I'm going to change colors here for this graph. So y is negative 2 for this intercept. I'll continue on this bottom one here. If I make my y value be 0, so now we're going to leave the x values alone and pretend they're back here, and we're going to cover up our y values. So if I pretended my y value is 0 in both of these, kind of makes 2 times 0 go away. I would just have for my top equation here, if this was gone, if this part was gone, I'd have just x equals 3. And down here, if this part was gone, I'd have x equals 4. These give me my x-intercept. So x equals 3 was the first one. I would connect this line here. And on the second one, which I'm graphing in purple, I would have x equals 4. And graph that, and I would connect that line. That's just one way I like to have kids graphing lines. And when I do that, that's called the intercept method. Is it fair game to type those into Desmos and check them? For sure, you can do that. Now, we're looking for a solution. What does a solution look like for one of these types of systems, if you will? Remember, system means there's like 2 of them there. And solution means the answer. We are looking for an x, y coordinate that if you had a number for x and a number for y, you could plug them into all the x and y spots, the x's and the number for the x and the x's and the number for the y and the y's. And when you did all that math for each of those equations, the top answer would come out to 3 and the bottom answer would come out to 4. Now we could do some guessing and checking, but it looks to me like if we graphically looked at this, we'd find that answer here. My only concern right now is either my lines aren't too straight or it looks to be crossing at kind of a yucky number. Now, I know if you were on Desmos, you could just click that little dot and magically you'd get the answer. I'm going to estimate it just by using my scale. So I had 1, 2, 3, I'm going to say like 3.5 for x. And my y value, how about like negative 0.5? That is my guess. Okay, so this is just me not using Desmos. Could you graph both of them and see if it matched? Yes. Could you also take this value for x and plug it into any of these? And take this value for y and plug it into here? Yes. And if you did that math, it should match up and make the 4. But I'm going to show you a couple different ways we can actually solve this algebraically. There are 3 different methods. Let's take a look. One method we can use is called the same value method or equal value method. That involves getting one variable alone here. So I'm going to look at x just because it's kind of all by itself and not messy. I'm going to get this equation solved by itself. So I'm going to get this 2y to go over here. I want to get these x's all alone so they have the same value alone on both these equations. So my top one would become x equals 3 minus 2y. My bottom equation would become, if I added the 2y over, except a plus 2y, it would become x equals 4 plus 2y. With same value method, we have the same variable alone, so we could say we know x is the same as x. They're the same variable. So we're going to put those equations equal to each other. So I'd have 3 minus 2y equals 4 plus 2y. Now I want to solve this. So to get the y's on one side, I'm going to go ahead and add 2y to both sides here. At the same time, I'm going to save a step and subtract 4 from both sides as well. That gives me these cancel, so I have negative 1 on this side, and 4 minus 4 cancels, and I'm left with 2 plus 2 is 4y. When I get y by itself, I divide by 4 here. I know that negative 0.25 is what y will be. Now with this system of linear equations, notice how we talked in the beginning. You have x's and y's this time. That's our main difference when you compare it to section 1.5. So when you want an answer, we want an answer with an x and a y. So I have my y, I need to find the x. I'm going to put this negative 0.25 in for any one of these y's. I'll go in this one, for example. So I would have x will be equal to 4 plus 2 times, I know y is negative 0.25. Think of that as a quarter. So I would say x will be 4. If I had 2 quarters, that'd be 50 cents. And a positive times a negative is a negative, so I would subtract 0.5 or 50 cents. And 4 take away 0.5 would be 3.5. I now have my x and my y value, so we would say the solution is 3.5 comma negative 0.25. Let's go back and compare it to my graph. Remember, I was just estimating on the last slide. And I had the 3.5 matching here. That number was good. My y value is a little off, so we now know I would change that to a negative 0.25. And it was close here. I know a Desmos answer would have given you the perfect answer, but I just wanted to show you how graphically we can graph it on our own, and Desmos could do it to help us find that. So while this was a guess, it was pretty darn close. Another method is called the substitution method. In this method, it's going to be similar to the same values method, but I'm going to get just this x alone. So like I did last time, I'd move this over by subtracting 2y. And that will become x equals 3 minus 2y. Now we're not going to change the second one. You are welcome to change either of the equations and solve for either x or y at any time. But what I can do now is in my orange modified equation, anytime I see an x in the regular black equation, I can put 3 minus 2y in. So what I'll do is when I'm trying to rewrite this equation here, instead of writing the x, I'm going to put this 3 minus 2y in. So I would have 3 minus 2y, and then I'll keep writing the black equation up here, minus 2y equals 4. I will do some combining of like terms here. I've got a 3 on this side. Negative 2y minus 2 more y makes negative 4y. And I leave my 4. I'll subtract 3 from both sides to get my y variable alone. And 4 take away 3 is 1. Then my final step, I'll divide by negative 4. And look at that. My y is equal to negative 1/4, or negative 0.25. Not surprising, because that was the same y value that I got using the same values method, and pretty darn close to the one I had on the graph. Remember though, when you have the x's and the y's in this system of equations, you need an x and y answer. So since I have the y, I could go back and plug this number in for any y. I'm going to go do it into this one right here. I'm going to use this equation. So I'd say x equals 3 minus 2 times, I know my y is negative 0.25. Again, thinking of quarters, 3 take away 2 quarters. It's a negative times a negative, so it'll be a positive 0.5. And there I have my 3.5 for x. Same answer, different method. Finally, we have one of my favorite methods. It's called the elimination method. When you have two equations with two variables, you have the x and the y. Remember, we're looking for our solution then to have an x and a y. And we know the answer because we've solved it 3 times already now. We can say, hey, if they are lined up in what we call standard form is where you have a number in x plus or minus a number in y equaling a number. This is what we call standard form. If they're both set up like that, we can look for a variable to eliminate. And this one is set up so perfectly. With elimination, we would line up our 2 equations, and since they're ready, I'll set them up myself. I'm setting them up like this, and with elimination, you're going to add them together. So I'm going to put a plus sign like old school adding, and what's going to happen is x plus x is 2x. But these are special, and this equation or these systems of equations were set up for me nice this way. Sometimes you have to modify them, but 2y plus a negative 2y makes them go away, or they're eliminated. That's the brilliance of it, because now watch, 3 plus 4 makes 7, and I'm just ready to divide by 2 to get x alone. And not surprisingly, there it is again, my x is 3.5. Of course, as you've been told, because you have an x and a y in your system, we need an x and a y in our answer. So I'd still need to go plug in my 3.5 for x. I'll pick the top equation just for the fun of it. 3.5 will go into my top equation. I'll keep writing it. Plus 2y equals 3. I'll subtract 3.5 from both sides, which leaves me with 2y equals negative 0.5. And divide that by 2. That gives me y equals negative 0.25. For the 4th time, but hey, that method's pretty neat. When it comes to 1-6, example 1, try it. I'm not going to go over either of these. You may want to look for your answer key from your teacher, but again, you could use any method. Remember, you could graph, you could do same values method, elimination method, or substitution to solve for x and y. Finally, you may want to take a second to pause the video and read through this situation. We have a gentleman who's mowing and walking dogs to earn money. He wants to earn at least $200. So we're going to call x mowing and y walking. It tells us to define the variables. That's the 2 things he's doing, so we're going to use x and y. Now we want to write inequalities. Remember, inequalities are those like gator or inequality symbols. So they tell us he earns $20 to mow, so I'm going to say $20 for every yard he mows, plus $10 for every dog he walks, 10y. He wants to earn at least $200, so more than would be great, equal to would be plenty. There's one equality or inequality or constraint we could say he needs to meet. He also he can only work 20 hours a week. Got to get that schoolwork done. So any mowing plus any walking must be less than or equal to 20. Finally, it says he has to walk the neighbor's dog at least 5 hours a week. So his walking y must be greater than or equal to 5. Now there's 2 inequalities that are constraints that kind of go unnoticed sometimes. He can't negatively mow lawns or negatively walk the dog. So we want to also say that y is greater than or equal to 0. He must walk 0 or more, and he must mow 0 or more. He can't negatively mow. Now, magically, I've graphed each of these inequalities. When it comes to these, we are shading. So we have x's and y's, and we want to shade where these are true. So for example, when y is greater than 0, that means I want all the numbers above here. When x is greater than 0, I want all the numbers to the right of it. When x plus y is less than or equal to 20, that's this purple one, I want it below it, because 0, 0 would definitely be less than or equal to 20. Same thing with y is greater than 5, has to be above here. We want to find the zone where all of these shadings would overlap. So I've indicated the area I need to shade for each of these lines by arrows. So I left the black one to go over with you. If 0 and 0 were plugged into this equation or this inequality, that would not make me more than $200. Therefore, I don't want to go left, I'd want to go right. This would be my zone where I would meet all my constraints. And that